Something just slipped past Mars that shouldn't exist in our neighborhood. An object from another star system, blazing with a brilliant core and wrapped in a glowing cloud of gas thousands of kilometers wide. But here's what's making scientists uncomfortable. It's missing the one thing every comet near the Sun should have. China's Tianwen-1 orbiter captured it first, released the footage immediately, called it breaking news. Meanwhile, NASA's Mars Reconnaissance Orbiter, equipped with a camera so powerful it can spot individual boulders on the Martian surface, also photographed this visitor during the same window. Those images, still locked away. Officially blamed on a government shutdown, but the timing creates questions nobody seems willing to answer directly. So we're left staring at grainy pixels from China while potentially crystal clear frames sit in digital darkness, which forces us to ask, why does our sharpest view of a cosmic stranger look like it was photographed through frosted glass? And what's hiding in the data we're not allowed to see? Because when a visitor from the stars breaks every rule we know about comets, and its clearest images never reach the public, we're not just dealing with a scientific mystery anymore. We're dealing with something that might reveal more about us than about what's out there. Let me paint you a picture of what just happened. Right now, this very second, there's a spacecraft silently circling Mars, not looking for ancient rivers or mapping craters. Its camera was aimed outward, into the void, tracking something that formed around a completely different star, something that traveled through interstellar space for possibly millions of years just to pass through our solar system once. The China National Space Administration released imagery that set the internet on fire. Their Tianwen-1 Mars orbiter had captured 3I Atlas at roughly 29 million kilometers away. That's 77 times farther than the Moon is from Earth. And yet they got it. This marks the first time humanity has ever publicly seen an interstellar visitor from a Martian perspective. Think about that. For thousands of years, we've watched comets from one vantage point, Earth. Now we're observing from multiple worlds. We're becoming multi-planetary observers whether we fully realize it or not. The State Council of China made sure everyone knew this was their achievement. They emphasized this was the only Mars-side data available to the public at that moment. And they weren't lying. NASA's high-resolution camera, far more powerful than anything China has in Mars orbit, also captured frames during the same observation window. Those frames remain unreleased. The explanation involves bureaucratic delays from a government shutdown, which sounds plausible enough. But it creates an uncomfortable vacuum. One nation shows the world what they found. Another nation's superior images sit in darkness, and the narrative writes itself. What did the Chinese imagery actually show? A bright, concentrated core surrounded by an enormous glowing cloud, a coma stretching thousands of kilometers across space. So far, completely expected. When a comet approaches the Sun, heat causes frozen materials to sublimate directly from solid to gas. This creates that signature fuzzy halo we associate with comets. But here's where your brain should start asking uncomfortable questions. There's no tail. None. At least not in any publicly released imagery, including these new Mars side views. When a comet heats up near the Sun, it doesn't just create a coma. The solar wind, that constant stream of charged particles flowing outward from our star, pushes gas and dust away from the comet. Radiation pressure acts like an invisible hand, sweeping material into two distinct tails. One made of ionized gas, glowing blue and pointing directly away from the Sun. Another made of dust, curving slightly as particles follow their own trajectories. These tails can stretch millions of kilometers behind the comet. So why doesn't 3I Atlas have one? Or does it? And we're just looking at it wrong. Is the imaging equipment not sensitive enough? Is the geometry all wrong, with the tail pointing directly toward or away from the camera, making it invisible? Are the dust particles too large to be swept into a visible stream? Or maybe, just maybe, this object isn't behaving like a normal comet at all. Let me give you the stakes here. 3I Atlas is only the third confirmed interstellar object ever detected in our solar system. Third, after Oumuamua in 2017, which looked like nothing we'd ever seen and sparked endless debate about its nature. After 2I Borisov in 2019, which at least had the decency to look like a proper comet with a visible tail. Now we have 3I Atlas refusing to play by the rules. This isn't just about pretty pictures from space. This is about who gets to define what we know about the universe. When only one dataset exists in the public domain, that dataset becomes truth by default, whether it's complete or not. The high-resolution imaging camera on Tianwen-1 captured 3I Atlas between October 1st and 4th of 2025. The spacecraft was positioned roughly 30 million kilometers from the visitor. To understand that challenge, imagine standing in Los Angeles trying to photograph a basketball in New York City. Now multiply that difficulty by several orders of magnitude and place both objects in the vacuum of space. What emerged was both expected and deeply puzzling. A bright, intensely concentrated nucleus at the center, exactly what you'd expect from a comet's solid core. Surrounding this, an enormous coma extending thousands of kilometers in all directions. Again, textbook behavior. This is Comets 101. Frozen chunk of material, sun heats it, volatiles boil off, coma forms. Simple physics, except the final act is missing. When a comet approaches the sun, the story doesn't end with coma formation. The solar wind, traveling at roughly 400 kilometers per second, slams into the expanding gas cloud. These charged particles ionize the gas, creating glowing plasma that gets swept into a tail pointing directly away from the sun. Meanwhile, dust particles experience radiation pressure, the physical force of sunlight itself pushing them outward, forming a second tail that curves gently. That's the classic model. That's what we see with nearly every comet venturing into the inner solar system. Hale-Bopp in 1997 displayed spectacular dual tails visible to the naked eye. Comet NOS in 2020 created similar structures captured by millions of photographers. Even Tuai Borisov, the previous interstellar visitor, showed a proper tail when it passed through in 2019. The physics is robust, the observations are consistent, the predictions are reliable. So why is Theia Atlas breaking this pattern? Before we tumble down the rabbit hole of wild explanations, consider the technical limitations. The camera aboard Tianwen-1 wasn't designed for this kind of observation. It was built to image the Martian surface, to resolve geological features like craters and layered deposits. Pointing this instrument at a faint, distant object in deep space is like using a microscope to watch birds. It might work, but you're operating outside the equipment's intended parameters. The camera's aperture measures approximately 8.7 centimeters across. Respectable for planetary imaging, but relatively modest for deep space astrophotography. Contrast this with dedicated sky survey telescopes on Earth, which often sport mirrors exceeding a meter in diameter. Collecting area matters when you're trying to gather photons from faint objects. Then there's geometry. The spacecraft orbits Mars in a specific plane. When it pointed at Theia Atlas, the viewing angle depended entirely on where both objects happen to be in their orbits. If you're looking at a comet with the sun behind you, you see it fully illuminated, and any tail would be visible extending away. But if the geometry is different, if the sun is to the side or behind the object, shadows appear, features become harder to distinguish. A tail pointing away from the sun might appear foreshortened or completely invisible. Stray light presents another challenge. Mars itself reflects enormous amounts of sunlight. Even though Tianwen-1 orbits above the atmosphere, the planet is right there, a massive glowing sphere contaminating the field of view. Any stray photons hitting the sensor wash out faint features, making subtle structures like a tenuous tail impossible to detect. The Chinese statement mentioned that Theia Atlas appeared 10,000 to 100,000 times darker than typical Martian surface targets. 10,000 to 100,000 times darker. That's the difference between photographing a sunlit desert and trying to capture shadows in a cave. So maybe the tail is there? Maybe it's just too faint for this camera to detect. Maybe it's pointing in an unfavorable direction, aligned with our line of sight, compressed into invisibility. Maybe the dust particles are larger than normal, measured in millimeters rather than micrometers, and they don't respond to radiation pressure the same way. Larger particles have more mass relative to their surface area, so sunlight pushing on them becomes negligible. They'd fall back toward the comet or drift away randomly rather than forming a coherent tail. Or maybe, and this is where things get genuinely strange, the object genuinely lacks a tail. Maybe something about its composition, its thermal history, its age, or its origin makes it fundamentally different from the comets we're used to studying. But we can't know which explanation is correct based solely on coarse imagery from one camera. We need more data. We need different viewing angles. We need the high-resolution images supposedly sitting on a hard drive somewhere at NASA. The Mars Reconnaissance Orbiter has been circling the red planet since March 2006. For nearly 20 years, it's functioned as our premier eyes above Mars, equipped with instruments capable of resolving features as small as a dinner table from orbit. The crown jewel is HORICE, the high-resolution imaging science experiment, a camera so powerful it can distinguish individual boulders on the Martian surface. Its primary mirror stretches 50 centimeters across, significantly larger than the Chinese camera. That extra collecting area translates directly into sensitivity, resolution, and the ability to detect faint features against dark backgrounds. So when Theia Atlas swept past Mars in early October 2025, NASA pointed this instrument at the visitor. The spacecraft captured frames, the data downloaded to Earth, Scientists presumably analyzed what they received. And then nothing. No public release. No press conference. No imagery shared with the astronomical community or the general public. The frames exist somewhere in NASA's archives, but they remain inaccessible to the very people who funded the mission through their tax dollars. The explanation centers on a government shutdown. These shutdowns occur when Congress fails to pass appropriations bills, forcing federal agencies to cease non-essential operations. During these periods, NASA's public communications often go dark, data processing teams get furloughed. But here's the uncomfortable question nobody seems willing to ask directly. Why would a government shutdown prevent the release of already captured imagery? The data exists. The download happened. The files are there. Putting them on a public server requires minimal resources. We're not talking about launching a new mission. We're talking about sharing photographs. Meanwhile, lawmakers have apparently urged NASA to release the frames. Members of Congress want to see what American spacecraft observed, which suggests the delay isn't just routine bureaucracy. When China releases their Mars side imagery first and American data that could provide superior resolution remains hidden, it feeds a narrative. That narrative goes like this. China is open, transparent, sharing discoveries immediately. America is closed, secretive, holding back information for unknown reasons. If HiRISE captured Thurai Atlas with its full capabilities, those images would resolve details impossible to see in the Chinese frames. Potential dust jets erupting from the nucleus, evidence of fragmentation or structural changes, the faint outer edges of the coma, and critically, any indication of a tail, no matter how tenuous. The HiRISE team has decades of experience squeezing every photon of information from their data. They know how to enhance faint features, stack multiple exposures, subtract background stars and cosmic rays. If a tail exists, they'd find it, but we don't get to see that analysis. Instead, we're left with the Chinese data as the sole publicly available Mars side perspective, which gives it outsized influence on how this story gets told. In science, replication matters. Independent verification matters. When only one dataset exists in the public domain, you can't cross-check results, identify instrument artifacts, or build confidence through convergent observations. You just have to trust that the available data represents the complete picture. This situation highlights a crucial distinction often blurred in space exploration. There's a difference between first discovered, first analyzed, and first released. First discovered would mean the moment photons from Thurai Atlas hit the detector. That probably happened nearly simultaneously for both cameras. First analyzed means when scientists extracted meaningful information from the raw data. That analysis likely occurred within days for both teams. But first released, that's when the public learns what was found. And in this case, China won that race by default. Does it matter? You might argue that scientific priority should go to whoever publishes peer-reviewed results first, not whoever issues a press release quickest. But we don't live in a purely academic world anymore. We live in an era of instant information, social media amplification, and public engagement with science happening in real time. When millions of people learn about a discovery through news articles that shape the narrative permanently, the peer-reviewed paper appearing months later rarely receives the same attention. Space exploration has become a venue for demonstrating technological prowess and national prestige. The space race of the 1960s wasn't just about reaching the moon, it was about proving which system could achieve the impossible. That dynamic never disappeared, it just evolved. Today, China lands rovers on the far side of the moon, builds space stations, announces plans for crewed Mars missions. The United States maintains the International Space Station, flies advanced rovers on Mars, operates the James Webb Space Telescope. Everyone watches everyone else, comparing achievements, measuring capabilities. In this context, being first to release Mars side imagery of an interstellar object matters symbolically. It says something about transparency, efficiency, willingness to engage the public. The narrative becomes China showed us what they found immediately while America sat on the data. And narratives, once established, prove remarkably resistant to correction. Even if NASA eventually releases stunning images revealing unprecedented detail, the story will still mention how China released first during an American government shutdown. That qualifier becomes permanent. Here's where speculation becomes irresistible. What if the HiRISE frames show something unexpected? What if they captured clear evidence of a tail that contradicts the Chinese imagery? What if they reveal fragmentation, jets, or structural anomalies that raise uncomfortable questions about what this object actually is? I'm not suggesting conspiracy or cover-up. I'm simply noting that when data remains hidden while other data becomes public, human nature fills the gap with possibilities. We wonder what's being withheld and why. Let's confront the central mystery directly. Where is the tail? When a comet ventures into the inner solar system, we expect certain behaviors as reliably as we expect water to freeze at 0 degrees Celsius. The sun's radiation heats the nucleus. Frozen volatiles sublimate. Outgassing creates pressure, forcing material to escape. Gas molecules carry dust particles with them, creating the coma. So far, Thurai Atlas follows the script perfectly. But then the solar wind should take over, sweeping material into distinct tails. And that's where our visitor goes off script. The solar wind consists of charged particles streaming outward from the sun at hundreds of kilometers per second. This isn't a gentle breeze. It's a supersonic plasma flow powerful enough to create Earth's magnetosphere. When this wind encounters neutral gas molecules in a comet's coma, it ionizes them. Once ionized, the gas becomes sensitive to magnetic fields embedded in the solar wind. These fields grab the ionized material and drag it away from the comet, creating the characteristic blue iron tail pointing directly away from the sun. Simultaneously, dust particles experience radiation pressure. Photons from the sun carry momentum. When they reflect off or are absorbed by dust grains, they transfer that momentum. For small grains measured in micrometers, this force can be significant. The pressure pushes the dust away from the nucleus, creating a curved dust tail. This is textbook physics. We can calculate expected tail length, brightness, and shape based on the comet's distance from the sun, its outgassing rate, dust to gas ratio, and solar wind conditions. For a comet like Thurai Atlas, passing relatively close to the sun, we should see substantial tail development. The fact that we don't demands explanation. First, consider observational geometry. If the tail happens to point directly toward or away from our viewing angle, it would appear foreshortened, potentially compressed to invisibility. Imagine looking down the length of a rope versus seeing it from the side. From the side, the rope's full length is apparent. From the end, you just see a dot. The Mars side observations don't automatically solve this problem. They provide a different vantage point, but that vantage could still align poorly with the tail's orientation. We'd need observations from multiple directions, preferably perpendicular to each other, to rule out geometric effects conclusively. Second, instrument sensitivity remains a limiting factor. Both cameras were imaging an extremely faint object at enormous distances. If the tail exists but radiates at surface brightness levels below the detection threshold, it simply wouldn't appear. Every detector has a noise floor, a minimum signal level required to distinguish real photons from random electronic fluctuations. Push below that threshold and you see nothing but noise. Third, consider composition. The James Webb Space Telescope observed Thurai Atlas spectroscopically, analyzing the light from its coma to determine chemical composition. The results proved surprising. The carbon dioxide to water ratio measured approximately 8:1. That's extremely unusual. Most comets show water as the dominant volatile, with carbon dioxide playing a supporting role. But Thurai Atlas flips that relationship. Why does this matter for the tail? If the nucleus contains abundant carbon dioxide, but relatively little water, and if the dust is bound more tightly or composed of larger particles, you could end up with vigorous outgassing that creates a large coma, but doesn't produce much visible dust tail. Carbon dioxide sublimates at lower temperatures than water ice, so it activates farther from the sun. By the time Thurai Atlas reached closest approach, maybe it had already exhausted its easily accessible carbon dioxide, reducing outgassing rates and tail production. Fourth, the possibility of large dust grains deserves serious consideration. If the nucleus sheds predominantly millimeter-sized or larger particles instead of micrometer-sized grains, those particles wouldn't respond effectively to radiation pressure. They'd have too much mass relative to their surface area. Instead of being swept into a tail, they'd follow ballistic trajectories, falling back toward the nucleus or drifting away slowly in unpredictable directions. You'd get a coma from the gas and these larger particles, but no coherent dust tail structure. Fifth, consider evolutionary age. Perhaps Thurai Atlas is an old, depleted comet that lost most of its volatile inventory during previous encounters with stars. If the surface became coated with a refractory lag deposit, a crust of non-volatile material left behind as ice's sublimate, then activity would be suppressed. You might see some outgassing from cracks or fresh exposures, enough to create a coma, but not the vigorous, sustained activity needed for tail formation. The final possibility, the one generating the most controversy, is that Thurai Atlas isn't a typical comet at all. Being interstellar changes everything. This object formed around a different star in a protoplanetary disk with potentially different chemical abundances, temperature gradients, and formation conditions. It spent millions or billions of years traveling through interstellar space, exposed to cosmic rays, collisions with gas and dust, and radiation environments we can barely imagine. Maybe interstellar objects simply don't behave like solar system comets. Maybe the assumptions we've built from studying our own system's comets don't apply to visitors from elsewhere. Some voices, including physicist A.V. Loeb, have even raised the possibility of artificial origin. But based on current observations, there's no compelling evidence for anything other than a natural celestial body. The absence of a tail, while puzzling, doesn't constitute proof of artificial construction. It's an anomaly requiring explanation, not a smoking gun for extraterrestrial technology. Science demands extraordinary evidence for extraordinary claims. So far, we don't have that evidence. What we have is an interstellar comet that refuses to behave normally, and that should be intriguing enough without invoking aliens. The implications extend beyond this single object. If we've misunderstood something fundamental about tail formation, dust grain dynamics, or comet composition, our models need revision. If interstellar objects behave differently from solar system comets due to their origins and histories, we need new frameworks for understanding them. And if geometric or instrumental effects explain the missing tail, we need better observational strategies to avoid similar confusion in the future. Right now, we're flying somewhat blind, making educated guesses based on incomplete data, while the key missing piece, those Herice images, remains frustratingly out of reach. You might reasonably ask why any of this matters. An interstellar object passed through. Spacecraft photographed it. The images show a coma but no tail. Science will eventually figure out the explanation. Why dedicate this much attention to a cosmic curiosity that doesn't directly affect anyone's daily existence? The answer operates on multiple levels, each expanding the significance far beyond a single confusing photograph. First, consider what 3I Atlas represents fundamentally. This is material from another star system. The atoms in that nucleus, the molecules in that coma, they didn't form from our sun's protoplanetary disk 4.6 billion years ago. They condensed around a different star, possibly earlier in the galaxy's history, possibly in a region with different chemical abundances. Studying this object gives us a window into stellar formation processes beyond our immediate neighborhood. We can compare its composition to solar system comets and ask, are they similar or different? If similar, does that suggest universal processes operating the same way everywhere? If different, what does that tell us about the diversity of planetary systems? The spectroscopic data showing a carbon dioxide dominated coma already hints at something interesting. That extreme ratio might indicate formation in a particularly cold region, perhaps beyond the carbon dioxide ice line in the parent protoplanetary disk. Or it could suggest the object came from a system with unusual chemical abundances. Each piece of information constrains possible histories, narrows the range of formation scenarios, and helps us understand not just the Atlas, but the broader population of interstellar objects that must exist throughout the galaxy. We've now confirmed 3 such visitors in less than a decade. How many more are passing through undetected? What can they teach us about the processes that build solar systems and create conditions for life? Second, the Mars side vantage itself represents a paradigm shift. For all of human history until approximately 2025, our observations of celestial objects came from one location, Earth's surface or Earth's orbit. We could only see the universe from our planet's perspective. That's changing rapidly. We now have spacecraft orbiting Mars, Saturn, and Jupiter. We have probes in the outer solar system and beyond. Each of these platforms represents a potential observatory, a new angle from which to view cosmic phenomena. The Tianwen-1 observations of 3I Atlas demonstrate the practical value of this multi-vantage approach. Different viewing geometries reveal different features. An object invisible from one angle becomes obvious from another. As our spacecraft network expands, we'll increasingly coordinate observations, triangulate positions, measure parallax, and build 3-dimensional models of transient events. Imagine a future where a new interstellar object is detected by Earth-based surveys. Within hours, we repoint Mars orbiters, Jupiter spacecraft, and outer solar system probes to capture the visitor from multiple directions simultaneously. The resulting dataset would be immeasurably richer than what we're currently wrestling with for 3I Atlas. But getting there requires missions designed with dual purposes. Primary objectives like Mars geology, plus secondary capabilities for opportunistic deep space observations. The fact that Tianwen-1 successfully captured 3I Atlas proves the concept works. Third, and perhaps most uncomfortable, is the question of transparency and data sharing in modern space exploration. The Chinese release of their imagery, framed as breaking news and heavily promoted by state media, achieved several goals simultaneously. It demonstrated technical capability, it showcased openness, and it created narrative advantage. Whether these were explicit strategic goals or fortunate side effects, the result remains the same. In the public's mind, China showed us what they found while American data stayed hidden. This matters because space exploration increasingly operates in a competitive geopolitical environment. The Cold War space race positioned achievements as proxies for ideological superiority and technological might. The current environment feels similar but more complex, with multiple nations and private entities pursuing independent capabilities. China has explicitly framed space exploration as essential to national rejuvenation and technological leadership. The United States sees maintaining its traditional dominance as crucial for economic and security interests. These competing interests don't always align with the ideal of open science, where data gets shared freely. The question becomes, does this competitive dynamic accelerate progress or impede it? Competition drives investment, innovation, and achievement. Without the space race, would we have reached the moon in 1969? Probably not. But competition also encourages secrecy, duplication of effort, and missed opportunities for collaboration. When data sets remain siloed, science suffers. When political considerations override scientific priorities, we make suboptimal decisions. The delayed release of high-rise imagery, whether due to government shutdown or other factors, represents exactly this kind of friction between national interests and scientific ideals. Think about it through a concrete analogy. Two mountaineering teams attempt to summit an unclimbed peak. Team A reaches the top first, but their camera malfunctions, so they only get blurry phone photos. Team B summits a day later with professional photography equipment, capturing stunning high-resolution panoramas. When Team A immediately publishes their blurry photos with a press release claiming first to summit, they establish the narrative. Even when Team B releases their superior images later, the story forever includes the phrase Team A reached the summit first, but only captured blurry images. Apply this to 3i Atlas and you see the problem. China released first with limited resolution frames. When NASA eventually releases potentially superior images, the story will always mention that China beat them to publication during a government shutdown. That becomes part of the permanent record, regardless of image quality or scientific value. Consider the missing tail in this context. If the high-res images reveal a tail that the Chinese imagery missed, that would be scientifically significant but narratively awkward. It would suggest the first Mars side perspective was incomplete, even if unintentionally. Conversely, if high-res confirms the absence of a tail with higher fidelity, that strengthens the mystery and validates the Chinese observations. Either way, we need that data to complete the picture. Operating with only one dataset in a matter this unusual feels like trying to understand a crime scene where half the evidence remains locked in a vault. The broader implication touches on data equity and publicly funded space science. If taxpayers funded the Mars Reconnaissance Orbiter through NASA's budget, do they have a right to timely access to the data it collects? Most would argue yes, within reasonable constraints for processing and validation, but timely becomes subjective when bureaucratic delays intervene. Meanwhile, Chinese taxpayers funded Tianwen-1 and their space agency provided immediate public access to results. This creates an asymmetry that shapes global perception of who practices open science and who doesn't. This single missing tail on an interstellar comet thus becomes a nexus where multiple issues converge. Scientific mystery meets instrumental limitations. Observational geometry intersects with mission capabilities. National space programs compete while needing to cooperate. Data transparency clashes with bureaucratic realities. And the public watches, trying to make sense of conflicting narratives and partial information. Let's pull back the curtain on the technology that determines what we can actually see from Mars. Understanding why an image looks the way it does requires grasping the complex interplay between camera specifications, spacecraft positioning, target geometry, and the fundamental physics of light. The Tianwen-1 mission arrived at Mars on February 10, 2021, representing China's first successful Mars orbital mission. The high-resolution imaging camera carries an aperture of approximately 8.7 centimeters, which determines how much light the telescope can gather. In astronomy, aperture functions as the fundamental limiting factor for sensitivity. A larger aperture collects more photons per unit time, allowing detection of fainter objects. This aperture is respectable for planetary surface imaging, where targets are large, close, and brightly illuminated. But for observing a faint comet tens of millions of kilometers away, it represents a significant constraint. Compare this to NASA's Mars Reconnaissance Orbiter, which entered Mars orbit in March 2006. The high-res camera features a larger primary mirror over 50 centimeters in diameter. That additional collecting area translates to improved sensitivity for faint targets. More importantly, high-res was designed specifically for ultra-high-resolution imaging with sophisticated detectors, precision optics, and extensive ground processing pipelines honed over years of operation. Both spacecraft orbit Mars in elliptical paths. When teams wanted to observe 3I Atlas, they had to wait until the spacecraft's position aligned favorably with the comet's position in space. You can't just point anywhere, anytime. The spacecraft has attitude control limits, power constraints, data storage limitations, and competing priorities. Think about the viewing geometry as a three-dimensional puzzle. The Sun occupies one position, 3I Atlas occupies another, and the spacecraft orbits Mars at a third location. The angle between the Sun and the target, as seen from the spacecraft, determines illumination. For 3I Atlas, the phase angle during observations determined how much of the coma and potential tail would be illuminated from the spacecraft's perspective. Additionally, the background matters enormously. The spacecraft isn't photographing the comet against a blank canvas. It's imaging through a field containing stars, galaxies, cosmic rays hitting the detector, and scattered light from Mars itself. Even though Tianwen-1 orbits above the atmosphere, Mars remains a huge bright object nearby. The Chinese statement noted that 3I Atlas appeared 10,000 to 100,000 times darker than typical Martian surface targets. The instrument was designed to photograph sunlit rocks and crater floors from orbit. Those surfaces reflect solar radiation efficiently. Now point that same camera at an object radiating 1/10,000th to 100,000th as much light. The exposure times required to gather sufficient signal increase proportionally, but longer exposures create problems. The spacecraft is moving at several kilometers per second in orbit. The target is moving along its trajectory through the solar system. Even with tracking to compensate for motion, anything beyond a fraction of a second introduces blur. Sensor saturation presents another challenge. The bright nucleus of 3I Atlas concentrates light into a small area on the detector. Push the exposure long enough to capture faint outer structures, and you risk saturating the pixels imaging the nucleus. Once saturated, those pixels provide no useful information and can bleed charge into adjacent pixels, creating artifacts. Consider also the spectral sensitivity of the detector. Most spacecraft cameras use silicon-based sensors optimized for visible wavelengths. These detectors respond strongly to red and near-infrared light, less so to blue and ultraviolet. If the tail emitted primarily in wavelengths where the detector is less sensitive, it would appear fainter than if it radiated across the full visible spectrum. Now apply all these factors to the question of the missing tail. If the tail extends perpendicular to our line of sight, it should be visible as a structure extending from the coma. But if it points toward or away from the observer, it becomes foreshortened, compressed along the line of sight into a much smaller apparent length. The Mars side observation doesn't automatically solve this problem. It provides a different vantage point, but whether that vantage reveals the tail depends entirely on the relative geometry. If the tail happens to point in a direction poorly aligned with both Earth-based telescopes and Mars orbiters, we might miss it from multiple perspectives. Here's an analogy. Imagine you're trying to photograph a firefly at night while standing next to a bonfire. The firefly produces faint light, but the bonfire floods your vision with brightness. Any light scattered from the bonfire into your camera overwhelms the faint signal from the firefly. Now imagine the firefly is also moving. Your camera was designed to photograph the bonfire's flames rather than distant insects, and you're not sure which direction to point. That captures some of the difficulty facing spacecraft trying to image faint comets from Mars orbit. None of this proves the tail is absent. It just explains why detecting a tail under these conditions represents a formidable technical challenge, and why the absence of a tail in the released imagery doesn't necessarily mean no tail exists. It might be there, hiding below the detection threshold, foreshortened by geometry, overwhelmed by the bright coma, or simply pointed in an unfavorable direction. But it might also be genuinely absent, which would tell us something profound about the object's composition and behavior. Distinguishing between these possibilities requires better data, multiple vantages, longer observation periods, and sophisticated analysis techniques. Right now, we're working with limited information from one camera not optimized for this task. Drawing definitive conclusions under those constraints risks mistaking instrumental limitations for physical reality. The chemistry of 3I Atlas might hold the key to understanding its strange behavior. The James Webb Space Telescope pointed its instruments at the interstellar visitor and captured spectroscopic data revealing the chemical composition of the coma. Spectroscopy works by splitting light into its component wavelengths, like a prism creating a rainbow. Different molecules absorb and emit light at characteristic wavelengths. By measuring which wavelengths appear enhanced or diminished, scientists can determine what gases are present and in what proportions. For 3I Atlas, the spectroscopy revealed a carbon dioxide to water ratio of approximately 8:1. That means for every molecule of water vapor detected, Roughly 8 molecules of carbon dioxide were present. This is extraordinary. Most solar system comets show water as the dominant volatile, with carbon dioxide playing a secondary role. Typical ratios might be 1 part carbon dioxide to 10 or 20 parts water. 3 Atlas flips this relationship dramatically, showing the highest carbon dioxide to water ratio ever observed among comets. What does this tell us? In a protoplanetary disk around a young star, different volatile species condense at different distances from the central star, creating distinct chemical zones. Water ice forms beyond the snow line, where temperatures drop low enough for water to freeze. Carbon dioxide requires even colder temperatures, freezing beyond the carbon dioxide ice line at greater distances. If 3I Atlas formed in the outer reaches of its parent system, beyond the carbon dioxide ice line, but in a region depleted of water, you could naturally produce a carbon dioxide-rich composition. Alternatively, the thermal history might explain the anomaly. If surface layers became heated and depleted of water ice during previous stellar encounters, but deeper carbon dioxide-rich layers remained intact, then current outgassing might draw primarily from carbon dioxide reservoirs. Carbon dioxide sublimates at lower temperatures than water, so you'd see carbon dioxide outgassing first and most vigorously. Now connect this unusual composition to the missing tail problem. If the coma is gas-rich but dust-poor, you might not produce a prominent dust tail. Dust tails depend on having substantial quantities of small particles entrained in the outflowing gas. But if the nucleus is primarily carbon dioxide ice with little dust content, or if dust particles are unusually large and bound tightly, then you'd get vigorous gas outgassing, creating a large coma while producing minimal visible dust tail. Think about dust grain size distribution. When material in a comet nucleus breaks down, it fractures into particles spanning a huge range from sub-micrometer dust grains to centimeter-sized chunks. The smallest particles respond strongly to radiation pressure because they have large surface area relative to their mass. Sunlight hitting these tiny grains imparts enough momentum to overcome their inertia, pushing them away and creating the classic dust tail. But larger particles measured in millimeters or centimeters have much more mass relative to surface area. Radiation pressure becomes negligible. These particles might get ejected by gas pressure, but then follow ballistic trajectories,